The Manus arm is an assistive robotic arm manufactured by Exact Dynamics. It has 6 degrees of freedom, 3 for translation, and 3 for rotation. It comes with an optional lift that can act as a 7th degree of freedom if needed. The gripper portion of the arm allows for a maximum clamping force of 4 pounds and can open to a maximum of about 3.5 inches. The Manus arm is light in weight and has a very tiny footprint when folded, making it ideal for mounting on a wheelchair. In fact, the Manus arm is compatible with most wheelchair models as it can be easily mounted to the side of most wheelchairs and runs off the power supplies found on a wheelchair. Out of the box, the Manus robotic arm comes with interfaces such as a joystick and a keypad. These devices allow the user to manipulate the position of the gripper in either joint or Cartesian mode. Joint mode allows individual control of each joint of the arm, but it is very non-intuitive as it is hard for a user to decompose a reaching motion in terms of required motion, such as the shoulder and elbow. Cartesian mode allows the user to command motions like up, down, left, and right, but again, this is not intuitive. The user is still required to compute the decomposition among the 6 overall degrees of freedom for position and orientation. This scenario shows that the user must constantly use the chart as a guide when controlling the robot in Cartesian mode. In this project, we are seeking to utilize visual feedback for both the user and the computer to allow for a more user-friendly system that leads to reduction in cognitive load for a user. The graphical user interface, also known as the GUI, is the link between the user and the robot. It includes live video feedback, as well as button-based menus for selecting and confirming commands. The link between the human and GUI is an important one for users with disabilities. Notice that in advanced control mode, the 12 rotation and translation buttons from the previous slide are consolidated into a single Go button. The approach button will move the arm in the direction of the hand, and the retreat button performs that opposite function. We have an assortment of devices for commanding the GUI and allows for a wide range of disabilities to be addressed. For example, speech recognition is convenient for users that have poor hand motor skills. A microphone is used for speech input, and the Microsoft Speech API is used for speech recognition. Notice how the dictated command is highlighted and how it is confirmed when the user hits the jelly switch.
Forward.
The buttons are easy to be commanded. For selecting a region on the live video feedback, the user can toggle a grid on the video feedback window, allowing the user to call out the index into the grid in order to tell the robot to recognize objects in a certain area. For users with gross motion in their hand, a trackball can be used to scroll through the live video window or through the different commands shown in the GUI. The user can confirm with the jelly switch when the object or the proper command is selected. For users with slightly better hand control, a touchscreen interface can be used to navigate through the GUI or select objects from the live video window. For users with slurred speech and poor hand control, we are integrating a head tracking device that will allow commands either in 2 dimensions for interacting with the GUI or in 6 dimensions for interacting directly with the robot. Let us see how the system works when trying to pick up this Nestle water bottle off the table. When the user selects an area on the video feedback window, the computer tries to recognize the object. In this case, the object turns out to be too far away to recognize, so the system tries to perform some gross motion in order to center and zoom in on the object. Before it can do that, it must first determine how far away it is from the object. The robot does this by moving laterally, simulating what is called stereo vision. The robot then uses this rough distance information to approach the object so it may begin object recognition. When the robot can successfully run object recognition, it can determine the required motions to align itself precisely with the object. This is the fine motion phase of the robot's motion. Once this is completed, the user can then command the robot to approach the object so it can be grasped and brought back to the user. Let us also see the case in which an object is on the ground. Here the robot is performing the appropriate rotation and translation movements to grab the remote control. Once the object has been grasped, it can be brought back to the user. This demonstration shows that the robot will go to pick up a selected object and won't just go to a fixed point in space. Here we can see that the robot is able to distinguish between the two bottles as it picks up the Nestle water bottle. Now let us see how the robot works when the water bottles are switched. The robot is still able to recognize and retrieve the correct bottle successfully.